Hello, this is Ms. Nichols in a very cold classroom recording this video on Kirchoffs Laws. The essential question for this video is how can I solve a complex circuit quantitatively, so using math in a way that is probably quicker than the other ways that I taught, so a nice shortcut for you. So the first thing you need to do when you're given a circuit diagram is you need to define what variables you're going to use in these equations that we're going to make, including the direction of those variables. So you need to kind of make a prediction about what's going to happen in this circuit. And if you've looked at enough circuits, you can probably make a pretty good prediction, but it's not the end of the world if your prediction ends up being wrong. So for starters, the voltage is going to increase at every battery. So I'm going to have a positive V value at all the batteries. And we're going to define, our resistors as the places the energy is being used. So I'm going to put negative voltage values for all of my resistors. The current in the circuit is another variable that we need to define. And the current should be constant in any continuous wire, right? Because of conservation of mass, we're not allowed to gain or lose electrons. So we just need to define as many different currents as we have sort of paths in our circuit. So I'm going to define I1 there that goes through R1. It would also be the same as the current that goes into VB from the bottom, because that's all continuous wire on that side. I'm going to define a variable I2 as the current that flows downwards through that branch of the circuit with R2 in it. And then I3 is going to be the current going through R3 and around the side of that loop. Again, you want to make a best guess at which direction you're expecting the current to flow in these wires. If it turns out your guess was wrong, when we do the calculations at the end, you'll end up getting a negative value for the current that you calculated, and that just tells you your guess was wrong, but you can still use it. So then we're going to use two rules, Kirchoff's rules, to come up with the equations that we're going to solve to get our ultimate answer. The first one is called Kirchoff's junction rule, and it's exactly the same as the junction rule in fluids, so it should make sense to you. And the basic idea is the current flowing into a junction has to equal the current flowing out of a junction. This, again, is because of conservation of mass or charge. So you can make an equation for each junction in your circuit. For example, that top junction, you could write I1 equals I2 plus I3 because you have I1 going in and I2 and I3 going out. You could also write an equation for the bottom junction, and that would look something like I2 plus I3 equals I1. You can see those equations are identical essentially, but the point being that you can write this equation for any junction in your circuit. The second rule that you'll need to write equations for circuits is called the Kirchoff's loop rule. And this rule says that the potential difference around any closed loop is always zero. So the amount of energy that an electron gains moving through a loop is going to be equivalent to the amount of energy that the electron loses going through any loop in this circuit. And this, of course, comes from conservation of energy. So when you take a circuit, you can draw loops all over the circuit. Each loop is basically a path that connects back to where it started. So one possible loop you could draw is shown in yellow. You could draw a different loop shown in green, or you could draw a third loop shown in purple in the circuit. So you can imagine bigger complex circuits might have more loops. Then you're going to write an equation showing conservation of energy for each loop of your circuit. And as you're doing this equation, you do have to pay close attention to what your signs are, and I'll show you that in just a minute. So for that yellow loop, I would write an equation that basically says VB, so I'm going to gain energy at VB, and then I'm going to lose energy at V1, so minus V1, and then I'm going to lose energy at V2, minus V2, and then add those guys together, and that should be equal to 0 by Kirchoff's loop law, or loop rule. The second loop, the green one, is going to look similar, positive VB, negative V1, negative V3, and then we go back to the battery, so that's equal to 0. And you can also write an equation for that purple loop, which is kind of a funny loop because it doesn't have any batteries in it. So the funny thing about this loop is that the loop includes going through that battery, or sorry, that resistor R2, sort of the backwards from the direction that you predicted. So while you would normally define going through a resistor as negative voltage, I'm actually going to put that V2 in as a positive value because I'm going reverse through it. Like imagine if you were an electron being forced upstream through that resistor, you're going to be gaining energy going that direction. So that third equation would look like V2 positive and then minus V3 because we're going through that one in the normal direction equals 0. Once you have your equations, you can just substitute in any known values and solve them simultaneously. You are going to need one equation per unknown variable, if you remember that from algebra class. And you want to make sure that all of the unknowns are in the sets of equations somewhere, otherwise you're not going to be able to solve for them. Once you have your equations chosen, you'll substitute in any of the known or given values. A note about this, if you don't know anything about the R value, if you are given R values, but don't have information about voltage drops across individual resistors, you can use IR, the product of current and resistance in a point in space, instead of the V in the loop equations. And this is from Ohm's law. Since V is equal to IR, at any point in space, the V can be replaced by I and R. Then you're going to combine the equations and you're going to solve them simultaneously. So for this circuit that we've been looking at through this whole slideshow, let's say we are also given the following information. R1 is 40 ohms, R2 is 64 ohms, and R3 is 12 ohms, and the voltage provided by the battery is 9 volts. This is pretty typical because you tend to know the battery voltage and you tend to know the resistance values that you've put in your circuit. So things you might want to know. Well, you might want to know any of the current values or any of the voltage values. Usually I go through the trouble of solving for one of them and then I use Ohm's law to find the other. You could make a bigger, more complicated set of equations with more variables in it, but I usually simplify by like, I'm going to find all the I values and then for whatever V's I need, I can use Ohm's law at the end. So I've got my equations. I have 3 unknowns that I need. I want to know I1, I2, and I3, so I'm going to need 3 equations. The way I chose those equations is I made sure that I had 3 equations that I could get, that I could make sure that I got I, 1, 2, and 3 out of. The way I got them is, so I took one of the loop law equation, sorry, one of the junction equations, and then 2 of the loop law equations. And then for those 2 loop law equations, for V1 and V2 and V3, I substituted in I1 times R1, because I know R1, and I2 times R2, and I3 times R3. So I rewrote those equations as shown below. I1 equals I2 plus I3 stays the same. And then in the next one, I substituted in the known values. So I know my battery voltage is 9. And instead of V1, I wrote I1 times R1, which is I1 times 40. And then I've got I2 times 64 equals 0, etc. You can see how this kind of comes together. So at this point, we have 3 equations. We've substituted in using equations that we had to get 3 unknowns and 3 equations. And at this point, now you get to do your math, solving simultaneous equations. So for example, you could take, since you know I1 is equal to I2 plus I3, in the second equation, I could replace that I1 with the I2 plus I3 algebraically. And then you could solve for I2 and plug into the third equation. Or you can solve the third equation for I2 or I3 and plug it in. But eventually you're going to be able to narrow it down to a single equation with a single unknown variable, at which point you'll be able to get the value for that variable and then work your way to get the other 2 variables. And as I mentioned before, once you know all your I values, then you can use Ohm's law back with the R values that you found, or the power equation, of course, to calculate any other unknown variables. So there it is. It's the heavy math solution, and you still do need to understand the concepts, but this may save you some time, especially if you have super big, complex circuits beyond the level that we'll be dealing with in this class, but things that you might see in college. Thanks for watching. I forgot that I had one more slide, which is this one, where you get to review your essential question and read the Calvin and Hobbes. So thanks again.